Yes, I need that. It's being recorded. Okay. All right. Good afternoon, everyone. Welcome. Some of you are moving around. Before we get started, are there any questions or anything you'd like me to follow up on from last week, Thursday? Okay, today we are going to start out with a little bit of a review. Except why is this? Here we go. We'll talk about white noise and random walks, and then we're going to get into this class of models called ARMA, which is two different bits. There's an autoregressive and their moving average. Those can be treated as individuals, or they can be combined into these ARMA's models. And then we'll talk about using autocorrelation function and the partial autocorrelation function for identifying model orders or possible forms of models. We talked a little bit about that on Thursday when we were discussing the ACF and PACF, so we're going to pick up with that. If you'd like, you can follow along. This should take you to the R code. Some of it is definitely repeated from last Thursday. Okay, so who remembers what white noise is? Two things. Sorry, I've already got the answers up here. Let's go back. White noise. What's that? That's one form of white noise.
Okay. Oh yeah.
Less restrictive. Two things. What was that, Nicole? Yes. That's generally what we think. What else? What's the expectation for white noise? Of a white noise sequence, I should say. 0. Yep. Yeah. So independent, Nicole got that bit, identically distributed with a mean of 0. And remember that form is flexible. So I showed you this example. I just created a white noise sequence with a Bernoulli, just a coin toss here. So that value just jumps back and forth between -1 and 1, and the long-term mean of that series is 0. We're in this class and in most of the examples that you're going to see in the literature and elsewhere, they're Gaussian white noise, or just basically normally distributed error terms. You can think of it, some mean 0 and some variance. And in an autocovariance or an autocorrelation function, if the lag is 0, then it's just the variance, the correlation being 1, because it's just take this thing, replicate it, and say, what's the correlation of this thing with itself? 1. It's perfect, right? And if lags are greater than 1, or I'm sorry, yeah, greater than or equal to 1, you should essentially have no covariance, right? So ideally, here's a white noise sequence, here's an autocorrelation function, here's that goofy bar where it equals 1 at lag 0, but you can see for all these other lags, there's no autocorrelation in this example. Okay, we talked briefly about random walks. And remember, random walk is basically a situation where the value today just equals the value yesterday plus or minus some error. And typically we think of that error term as being white noise. So here's an example of a random walk, 100 values simulated. Errors are standard normal deviates. And here you can see that this has very strong autocorrelation out to many lags, 9 here in this case. And you will remember that time series that are kind of smooth have high autocorrelation out to large lags, and those that we think of as very choppy, like white noise, should have very little autocorrelation. And once you get to white noise, it's 0, because think about in sort of a limiting sense, if we put an exponent, or I'm sorry, just a modifier up here, a parameter in front, a multiplier, let's call it B, you're going to see that later in the course. As B goes to 0, this thing gets to be really choppy, and when this term goes away, xt just equals wt, and we just said that wt was white noise. So, right, so as this coefficient gets close to 1, you should see strong autocorrelation out to long legs. And as that coefficient gets much closer to 0, this is going to get pushed back, such that ultimately, you might see something that looks like this, right? But as we increase that series out here, you're going to see that longer and longer and longer. So this again should be a bit of a identification tool for you. If I hadn't shown you this and only showed you this, you might say, oh, that looks a lot like a random walk or something where there's some autocorrelated model like this where that coefficient must be fairly large. Okay. I think Eli, when she gets to some of her, she's got a slide in some of her decks where she's got the exact same model that she just simulates many different times. That's a random walk. And it does all these really different trajectories, none of which essentially look the same. And random walks, because of this form, they're super flexible. If we make this variance term large enough here, we could fit a lot of different shapes with a random walk. So just be aware of that as you're moving through life and thinking about this as an analyst. Okay, we talked a little bit about random walks. Now we're going to introduce this notion of a biased random walk, or what you also will hear is a random walk with drift. And that latter term is very common in genetics, thinking about allele frequencies. And in this case, all we're going to say is that the value today is the value yesterday, plus or minus some constant, plus or minus some error. Okay, so this bias or drift term is going to give you sort of the average rate of change per unit time. Okay. And I have some examples of that. So here now is a biased random walk where the bias term, I just gave it a 1. And here's the errors now at mean 0, but a variance of 4. And you can see that on average, that trajectory is going upward, but there are certainly times when it jumps down a little bit. Here it's jumped down a little bit, jumped down, here it went down several times, right? So I think if you stared long enough at that, you could convince yourself that, yeah, that is trending upward. So biased random walks are used all the time, especially in like population assessments, where oftentimes the thing of interest is trying to estimate what this like in an annual rate of change might be. So population viability analysis, this is a classic one. You fit a model like this and try to estimate what that bias term is. Here too is another example of the ACF for that function. And this one has very strong autocorrelation well past lag 20. And you may recall from last Thursday, when we started looking at these ACFs, I showed you one where this was just a straight line. It was just a deterministic flat line. And this had this very similar shape. So now you've got something that is quite a smooth time series. If you look at that, it's not going up or down a lot relative to that long trajectory it has. So it's got super high autocorrelation up to many lags. Okay. One thing to know, this would apply for a random walk as well. We talked briefly about this difference operator on Thursday. If you difference a biased random walk, what you should have is some constant, or in time series, we'll often refer to that as a level, sort of where we are here, plus some white noise. Okay, so let's just do that algebra. So here's our biased random walk. And we're going to take the difference of this. So we have to apply this difference operator to both sides. And remember what this difference operator says is it just says, take this and subtract a time shifted version of itself. So that's x of t. So we're just going to subtract x of t minus 1 here. And we'll subtract that here. These two terms are going to drop out. So on this side, you're left with u plus wt. And over here, you have the difference time series. So we've differenced a biased random walk, and it just looks like this level. So I'll show you what that looks like here. Okay, so there's our biased random walk, and all I did here was first difference that and plot it. And if you estimate the mean of this, you're going to see that it's about 1, which is this term right here. So using this logic, back this up one second. What happens if this is just a random walk? There was no U term here, and we first differenced it. What do we get left with? What's that?
Just white noise.
Yeah, right. We just said this term goes to 0, so here you have So first differencing, a random walk should lead you with white noise. The other thing that's kind of interesting about that, you just essentially you can think of differencing as sort of the discrete time version of a differential, right? Essentially taking a first derivative. With the random walk, you get this left over. In another one, you do it. If you reverse that process, you can think about what's essentially the reverse of differentiation, and it's integration. And if we're taking differences here, what would be the active? It would be a sum. So it turns out that if you basically back this up so we just have regular white noise. If you simulate a whole bunch of random deviates like this, white noise terms, and create a cumulative sum of these, you will have a random. And if you don't believe that, just open up an R situation right now and just say, R norm of 50 and make a cumulative sum of that vector, and you will get a random walk. Similarly, if you replace this with some non-zero mean, call it 1, and you created a cumulative sum of that, you would have a biased random walk with an average bias of 1. So sometimes, in fact, in lab, I think you're going to see that in some code. And the first time I saw that somewhere, I didn't believe it at all. I was like, I don't think that math works out. And then I had to kind of write out the recursion and show myself, oh yeah, you literally are just summing all these things up. Okay. All right. Any questions about any of that before we start talking about ARMA models? So white noise, random walks, and biased random walks, you're going to see a lot of in this class. And quite frankly, a lot just in general in time series. Okay, everyone ready to push forward here? Okay, let's begin this conversation of linear stationary models. We saw last week this notion that we could use these linear filters when we were doing classical decomposition to try to estimate this trend. And we saw that, just as we've seen even earlier today, that trend does not always mean just a straight line. A lot of this tends to be what people think of, right? Because we've been so ingrained with things like linear regression. Here, we're going to think about those kind of notions of linear filters or linear models with respect to this large class of models, autoregressive moving average or ARMA. You'll see that a lot. So let's begin with autoregressive models. These are widely used in ecology and environmental sciences, in particular because, as you're going to see, this notion of autoregressive means what we have today is some function of what we had in the past. That's really all an autoregressive model means. So basically, the way this works is we're going to define an autoregressive model of order P, and P is just an integer here. Greater or equal to 1, 1, 2, 3, 5, 20. And the way this works is for an autoregressive model of order P, we're going to have P terms here. So let's make P 3 for now because it makes this example. So now we have some coefficient, phi1 times x at t minus 1, plus phi2 times x at t minus 2, plus phi3 times x at t minus 3. Okay, we are always going to assume that this error term is white noise. And for convenience, this seems a little bit obvious perhaps, but if you tell me you have an AR3 model, we're going to assume that this coefficient here is not 0, because otherwise it's just AR2. Okay. It's also important here to point out that not all of these intervening terms need to be non-zero. So you could have an AR3 model where this coefficient was here and to be estimated. This one is actually a priori set to be 0. So this term just drops out, and then this term drops in again. One example where you might see this kind of commonly is you might have an AR12 model based on monthly data. And the idea is that what we observed this month is a function of what was going on last month, plus maybe a whole year ago, because we're dealing with perhaps annual plants. or something like that, or some annual animal that produces once a year. So if there were a lot 12 months ago, we might have a lot this year, that sort of thing. Okay, here's some examples of ARP models. So the first two there are both AR1. There's literally just one term here, and then white noise, one term here. So this one has a non-zero, non-one term, it's 1/2. This one has phi equal to 1, so it's just a random walk. Okay, so random walk models are autoregressive models. And anytime you think of autoregressive, you should immediately be thinking something today is a function of something else. Now, I should say, you will sometimes see these models written as t plus 1 here and t here. It doesn't really matter. You can just adjust your thinking any way you want. Typically, this is still left as wt here. So you take some value today, add something, and that's what you're going to get next time. The indexing doesn't really make a big difference. It's largely a matter of choice from the analyst's perspective. That latter form, where this is like t plus 1 as a function of t, you'll see much more in forecasting context. We're trying to make some guess about what's going to happen at some point in the future. Here's an AR2 model. That first coefficient is negative 0.2. The second one is 0.4. Okay. There's nothing particularly special about these models. AR1 models, though, whether it be with the coefficient or with an implicit 1, these models you're going to see a lot of in class in some form or another. Okay, so here's just an example of 4 different AR models. They just increase in order. 1, 2, 3, 4. Is there anything really radically different about these time series? I don't think so. So do you need all of this stuff to make it work? Sometimes, yes. Sometimes you might ask yourself, this doesn't look a lot different to me than this. And here we have 3 more parameters. We need phi2, phi3, and phi4. Could we not describe this time series or maybe this time series with an AR1 model? Sometimes you can't. Okay, remember we talked about this notion of stationarity, and there were 3 aspects we talked of if we were going to consider time series to be stationary. One was that we didn't expect to see any changes in the mean or the variance. We don't want things that go like this, like the PDO or something like that, or El Niños. We don't want things that go like this or like this, right? We don't want these obvious trends in there. We don't want things where the variance kind of blows up as we go along. We're looking for things that do not have any sort of cyclic or period to them. And I guess I already said trend, right? So one of the things that can be nice, because stationary processes sort of hold a special place in time series lore, and they have a lot of nice properties about them. So oftentimes we're looking for a means to very quickly identify whether a process, in particular ARP processes, are stationary. And to do so, we're going to invoke our friend the backshift operator, which I showed you before. So the first thing to do is to take an ARP model, and we are going to rewrite this using the backshift operator. And remember, I was going to bring in a better pen. Remember that that backshift operator on x of t just gives you, right? So the idea is when you see t minus 1 in here, we're going to replace that with a backshift operator. So the first step was to move all of these x's to the left-hand side of the equation, right? So now the equal sign is just moved over here. So this was just simple algebra. And now I've gone through, and every time I see a t minus 1, that gets a b. This was t minus 2, so that was backshifted twice. So we'll write that as b squared. We go on and on and on until we get to the p term, was 3 in our previous example. That'd be b to the p, x of t. And we can write all of this compactly in this form. This so far is purely a parlor trick. Just at this point, this should mean essentially nothing to you other than neat, Mark. Wow, exciting. The reason we're going to do that is because if we treat P as a number or a set of numbers, we can write out what we call this characteristic equation. So we basically treat this essentially goes away. This goes to 0, and we're going to solve this for B. And again, in this, it's a little abstract here, but it will make much more sense when we work through some simple math. To be stationary, all of the roots of this equation must be greater than 1. Okay. So let's start with that first AR1 model I showed you a few slides ago. So I said that this model says x of t equals 1/2 of x at t minus 1 plus wt. So now let's just do some algebra. Okay, same thing. I just moved all the x's over to the left-hand side of the equation. That's this step. Here I'm going to replace this with b at x minus or bxt. Now we're going to treat this as a number, right? Because I can multiply through here. So here I'm just factoring out the x. Right, so this just becomes 1 minus 1/2 t times x of t is here. We're going to set this bit to 0 and solve for b. Okay, so there's where we ended last thing. We'll set this to be equal to 0. We're going to drop that x. B is 2. So that model is indeed stationary because all roots are greater than 1. It just affords us this ability to solve this equation. It's literally just a convenience.
Okay, so like 17 to be 0 because like the expression means without it be 0.
Yep. So here we'll set this to 0 and this to 1. Essentially what we're doing. And I'll show you a couple more examples of how this will work. You can do this for any order P. At some point, it's going to get pretty hard to do because solving this one with 1 is pretty easy. For 2, there's a quadratic equation, so we can get that. But when you start to get 3 or 4, you're going to need ChatGPT or somebody else to help you. Okay, here's an AR2 model I showed you earlier, right? I said it was minus 0.2 times x at t minus 1 plus 0.4 x at t minus 2. So we'll do that same thing here. We'll replace t minus 1 with this bx2 or bxt. This is a t minus 2, so we need this b squared times x of t. We'll factor out the x. We'll set this equal to 1 and this equal to 0, and then we're going to solve for the b. Okay, so if you do that, and you put together the quadratic equation, I don't know how many of you remember that offhand, it's like minus b plus or minus 4, right? Anyway, B1 is about minus 1.35 and B2 is about 1.85. I'm rounding here because they're not exact. This model is not stationary because only B2 here is greater than 1. B1 here is less than 1. So that model is not stationary. You're going to see a little bit, maybe on Thursday and some moving forward in class. There's some functions in R that will allow you to simulate ARMA models by just giving it a P and a Q, and then you can tell it something about the variance of this error term. If you try to simulate from a non-stationary model using that function, it will warn you right away. It can do it, but it will say this is not stationary. So it basically goes through and does all this math in the background. It says yes, no. How about random walks? Anyone have a guess? Random walk stationary or no? Ben says no. Anybody else have a guess? Maybe. Let's yes or no. We go. Okay, let's find. We just do the same math here. Okay. So move the x's to the left side. Replace this with bxt. Factor out the x. We're going to set this to 0, that to 1, and solve. Okay. Here's where we left off. We do this, we do the math, b equals 1. So b is not greater than 1, it's equal to 1. So random walks are not stationary. And remember, we talked about that a little bit on Thursday about how they do these weird things where over time, like the covariance grows and grows as a function of T and all this weird stuff. Yeah. So random walks are not stationary. Not, never. This is a classic question that would come up in many cases. And you will have an opportunity somewhere in your career to prove someone wrong about this because they will insist that this is a stationary process. Actually, it's not. I can prove it to you. Okay. So anyway, this is a trick that you can do on, with a whiteboard or a piece of paper, as long as you pretty much have an AR2 or 1 model. But like I said, AR3 gets to be very difficult. AR4, I can't do any of that math. It's rare that you would have to do that typically. Like I said, most softwares now can just tell you. So it's not something you're typically going to be asked to do. Anyway, let's think about this notion though. And in particular, I want to focus just on AR1 models. So here's our AR1 model, very simple. I'm going to pause for just a second. Using this term phi here is really standard in time series literature. In class, when moving forward, when we see a lot of these models, you're going to see just a Roman letter B here. There's no difference. It's just a parameter. You can call it whatever you want. Okay, so we'd like a way to figure out, is there some parameter space for phi whereby we can determine that just by looking at this model instantly without having to do any of that algebra, you could just tell me yes or no. And there is. I'm going to tell you that. So let's think about this. Okay, so we're going to rewrite this equation just as I did before. Just moved all the x's over to the left, invoke the backshift operator, and just factor out the x. Okay, so this is the same thing you saw a little bit ago. This is where we were. Let's set x to 1 and w to 0. That says that in this case, minus phi times b is minus 1. B is going to be equal to 1 over phi. The only way we can get a stationary model out of this, remember where I said b has to be greater than 1, is to ensure that this term phi has to be somewhere between 0 and 1. Okay, right? If this is 1, what happens? That's 1 over 1. That equals 1. Nope, that's no good. What if this is 2? That's 1/2. Nope, that's still not greater than 1. If this is 1/2, 1 over 1/2 is 2. Okay, now we get somewhere. That's where we were before. So now we know for any phi that's greater than 0 and less than 1, this model is going to be stationary. Okay, let's do the same math, but this time we're going to assume that phi is negative. So before it was positive, this is all exactly the same. So we're just moving things around, substituting in that b backshift operator, and here pulling it out by algebra. So there's where we were. We'll set this to 0, this to 1. Now we're trying to solve for b as a function of phi. Here we are again, but this time it's minus 1 over phi. So the only way you're going to get b greater than 1 is if phi is greater than minus 1 and less than 0. And technically here, you can make this less than or equal to 0. Because you know that if this phi term up here, if this goes to 0, that whole term goes away. What is that? What are we left with? White noise. Is white noise stationary? Yeah, there's no trend, no seasonality. It's just, it is very stationary. So what we can say here then is any AR1 model where the absolute value of that coefficient is less than 1 is going to be stationary. Okay, so from now on, any AR1 model you see, all you have to do is look at that phi term and you'll immediately know if it's stationary or not. Is the absolute value less than 1? Okay, here's a couple examples just to sort of get you thinking about this. Here's one. These are both AR1 models. Both have the same magnitude of coefficient. 0.7, but here it's negative, and on the left it's positive. Does anybody notice something in the kind of contrast between these two panels? Just again, think about back to day one, we were talking about just describing time series in words. The one on the left, say that again. Yep, that, it turns out, was just simulation luck, bad luck. This is, we know that this model is stationary, right? Because in absolute value, that's less than 1. This model is also stationary because in absolute value, that's less than 1. So we would expect there to be no trend one way or the other. We don't see seasonality, that sort of thing. How about, this looks a little bit seaside. Up, down, up, down, up, down, and then you get maybe 1 or 2 breaks, but there's this up, down pattern. This, you see much less of that. Negative AR1 coefficients have this tendency. They oscillate back and forth, -1, or, up, down, up, down, up, down. And it's because you're multiplying by a negative. So it's, you have a negative times a positive, that's negative. Now you have a negative times a negative, that's right. So it tends to jump up and down there, but then you've got some error on top of it. So when you see time series that have this rapid up and down pattern to them, really good chance that that first coefficient is negative. For general AR, you will see later when we start, you can get some other activity in here. If you've got a lot of other terms, some of it starts to have to do with the magnitude of this. So if this is, like if that's -0.7, and the AR2 term was, maybe 0.1, and clearly this has roughly 7 times the effect of 2 time periods ago. So the magnitude of that definitely plays a role as well. Okay, here's a case where I have 2 different stationary models, both AR1. They're both positive. This one is 0.1 and this one is 0.9. And I purposefully plotted these with the same range on the y-axis, so you can see sort of that behavior. Any generalizations here that folks see?
Pretty close towards the or whatever, and the 0.9 is not.
Yeah, so what Emma's saying, if you squint, you kind of look, this is sort of sitting in this range here, roughly between -2 and 2, and that's where we'd expect to see about 95% of these observations. This one is definitely swinging around. There's a wider range here. This one too, again, it's a little hard to say in squint. I'm gonna say this is perhaps a little more smooth than this one. Okay, so the idea here is, right, as this term goes to 1, what do we get? Random walk, yeah, you got it. What happens when this term goes to 0? White noise. So, right, so you can make this 0.05, then 0.01, and you're gonna see something here that looks really, really close to white noise. Make that thing 0.95 or 0.99 simulated, you're gonna see something that looks a lot like a random walk. Okay, let's talk about autocorrelation function again. Remember that this was basically the correlation between some vector of numbers and a replicated version of that vector that we've just shifted plus or minus some number of flags, okay? Here is the ACF for those first 2 I showed you. So on the top, that coefficient's positive 0.7, and here it's negative 0.7. There you can see what those time series are again. Here is the ACF for those. Okay, so what are some of the things you notice about this one? Yeah, all of these correlations are positive. Whereas down here, what's happening? every other thing, that thing switches from positive correlation to a negative correlation to a positive correlation to a negative. Because you've got a lot of values that are like positive, negative, positive, negative, positive, negative. So you can just imagine if it was truly that seesaw, and we shifted it one, it should have, you know, really good positive correlation with the other one. We shifted one more and it should be completely out of phase, so to speak. So when you see ACFs that oscillate like that, there's a really good chance that that first coefficient is negative. Remember we were talking a little bit too, when I was saying something the other day in class about that AR1 coefficient. You can think of this as sort of being analogous to a dampening coefficient on a spring. Look at these ACFs and you kind of get that. This one is just being damped right here. This one is oscillating, but slowly getting into here. Also, I'll point out, when I simulated these, this time series in simulation, I'm guessing is not 50, but probably 500, and I only plotted the first 50. And that was to ensure that I was getting really well-behaved ACFs here. That's why these confidence intervals are tiny, because the N here is not 20, it's much, much bigger than 20. Okay, here's those last ones we looked at. We're now positive 0.9, positive 0.1. And what do we see about these two in contrast to one another? How about this one? Yeah, we've got positive correlations or significant correlations at least out to lag 20. How about here? Maybe we got one at lag 1, and that's it. Okay, so when you see something that drops off very quickly, that suggests that this AR1 coefficient is relatively small. And when you have something where this goes on and on and on for a long time, that AR1 coefficient is going to be relatively large. Okay, we also talked about this partial autocorrelation where we remove that kind of interdependence. If A is like B and B is like C, then A is like C, and we're trying to remove that intermediate bit. Here now are a couple of models, both AR3, that have some relatively different behaviors, you might say. And here, this one is minus 0.7, 0.2, and 0.1. Here it's 0.7, 0.2, minus 0.1. Okay, here's the ACF and PACF, the ACF and PACF. Okay, this was the one this had that negative coefficient, so this thing is doing this funny oscillation and finally becoming damped. Here we just have this exponential decline. Here, it was positive, positive, negative, and now they're all looking zeros. Here it's negative, positive, positive, and all looking zeros. Gee whiz. Anyway, I'm going somewhere with this, trust me. Here now, I'm showing you the partial autocorrelation for 4 different AR models. AR1, 2, 3, and 4. And I'm wondering if any of you can spot a link between that order, 1, 2, 3, or 4, and lag K. Yeah. Can someone come up with an even more firm rule than that? Yep. How many is it here? How many is it here? So for AR, well-behaved AR models, again, in a very kind of asymptotic sense, the lag at which an ARP model goes to 0 should tell you where basically you're losing lag. So here, if you gave me a time series, I didn't even see the time series. Okay, you're like, here, I have some information. You don't get to see it, but I'll show you this PACF. If you showed me this and I saw this, I would say, I bet it's an AR4 model. Yeah.
So does that include stationary and non-stationary models?
Yes. Yeah, so there's no criterion here that these have to be stationary when you do this. I will also just issue a word of caution. Once again, see how teeny tiny these confidence intervals are here, because I simulated the bejesus out of this thing. I don't remember how long it is, but it is really long. And I did that so that we got these well-behaved PACMs. So sometimes this might be an AR4 model, and maybe like this one is not looking significant, or maybe that one is. So what I would do, we talked about this a little bit, is I might try to fit an AR3, an AR4, and an AR5 if I saw this type of structure, and let AIC or something like that tell me what the best option was. Because again, these are really asymptotic properties. You can think of kind of large sample sizes. Okay, so we're going to build up this table as we go along here. For ARP models, we saw that that autocorrelation function tends to tail off relatively slowly, which is also related to lag. But for this PACF, it cuts off, the significance cuts off after lag P. Okay, now I'm going to move on to moving average models. Any questions before I do about what we briefly covered with AR? Yeah, Lila. I don't want this confidence interval to necessarily be lower. That is just a byproduct of me simulating a really long time series. I simulated a really long time series so that these asymptotic properties of the PACF would generally hold true for these examples. If I had really just simulated like 20, a time series of length 20, this may not, you may have seen, yeah, something there, maybe there, you know, I may not have gotten a nicely behaved PACF.
So the PACF is not changed, but just a constant. Okay.
Yeah, I mean, some of this maybe, these may have changed, they would change some as I made this vector longer and longer and longer, right? I would get much better estimates of what these are. But yeah, because there's a square root of n in the denominator of the confidence interval, as you make that time series go longer and longer and longer, these things are shrinking like this. Okay, moving average models. You see moving averages sometimes in forecasting contexts. Admittedly, in environmental science, we do not encounter these very often at all. So I'm going to present them in class so that you get exposed to them, you get to see them. We're going to talk about ACF and PACF for moving average models as well. But we're not going to spend much time in class dealing with these. Usually you don't see them. They tend to have sort of a smoothing effect, not unlike that linear filter that we saw the first day in class. So you can use them in those contexts, but very little of what we cover for the rest of the quarter are you going to see moving average components. Okay, so we talk about moving average models as having an order Q, ARP, MA, Q. Just an integer, same thing. It's just 1, 2, 3, 4, whatever. And in this case, we treat our data as just a weighted sum of past error terms. So the first error term we don't give, this exists in the model, all ARP or all ARMA class model. But now we have a theta 1 times WT minus 1, theta 2, et cetera, et cetera, et cetera. Okay. And just like we said before, if we had an MA4 model, we would assume that this term right here, the fourth term, is not 0. But it is possible that some of the intervening terms could be 0. Okay. Oftentimes, you can think of these terms too as being scaled. So we said our value today is some function of some white noise today, plus some portion of white noise yesterday too. So you can imagine that somebody would want to model maybe intentionally where this has a larger coefficient than this because they want to weight essentially mistakes. These are errors, these are differences. The more recent ones have more importance than those that are a long time ago. So in a forecasting context, that makes sense. We maybe have some wiggle we need to induce this year. Boy, last year we were off by a lot. So we want to weight that heavily. 3 years ago or 5 years ago or whatever this number is, we were off a lot, but that was so long ago, it doesn't going to make a big deal in our forecast. So this coefficient could be relatively small. Okay, because we've got a whole bunch of white noise terms here on the right side of the equation. All we're doing is summing up some fractions of those. Every one, all of them. MA processes are stationary. Because white noise is stationary and all we're doing is adding up series of white noise. Yeah, we might be dividing some of those by half or multiplying some by 2 or something. But this is basically, you're just taking a whole bunch of white noise things and stacking them on top of each other. It's still white noise is basically what you're going to get. Here's an MA1 model, an MA2 model, where this one has a positive 0.7 coefficient. This one has a negative 1. And here you do see some of that oscillatory behavior as well, like we saw in the AR1 model. So negative coefficient, positive coefficient. Excuse me. Here are those two models. Here's the ACF in this middle column, and here's the PACF in this column. Here it looks like there was really no autocorrelation after lag 1. Well, for this one here, we didn't even see it at lag 1. Maybe there's some at lag 2, maybe at lag 5. So why do you think we'd see significant partial autocorrelation at lag 2 or 5? Based on a model that just was MA1. Don't overthink this. So I have 20 null hypothesis tests, or yeah, Ben.
This is just a you get the same value at 2 and 5 based on chance.
Yeah, for whatever reason, that when I simulated from this, I just got lucky. And when I ship those things off by 2 and 5 lags and control for that intervening correlation, I just got, yeah, here. This one's probably for real, but maybe not even. Okay, what's going on over here? Here we had MA1, maybe, well, of course at 0, it's 1. We know that. Maybe there's something at 2. Maybe we had 1 at 1 here. Okay, I'm going to show you this again. Now we're looking at the autocorrelation function, not the partial, but just the ACF for MA1, 2, 3, and 4. Same question as before. Any relationship between the order of moving average and that lag. Okay. Surely someone sees it.
+1 is the significant.
Yeah, it's really, in this case, like it's just 2 because again, this is that ACF plot, so it keeps sticking the 0 in here. No, but you're right? What's she saying? Here's MA1, there's 1 significant autocorrelation of 1 lag. Here's MA2, you see it at lags 1 and 2. Here's MA3, you see it at 1, 2, and 3. Here it's negative, but it's significant. And here it's 4. Yes, that barely crosses that line as it turns out. Yes and yes. And again, when I simulated these, they're really, really long, and that's why these things are so tight. So in theory, for MAQ models, that ACF should cut off after some lag Q. And that PACF, we say tails off slowly, maybe or maybe not, right? You saw some examples of that. I'll back up here. Yeah, maybe this does. That one tailed off pretty quickly. I think in both of these cases, these are the boxes to focus on. Okay, so if I handed you some ACF and PACF plots for a time series that you had never seen, you should be able to look at them and based on some behaviors of those, get an idea of what's going on. Okay, if you saw something cut off after lag 2, you might say, oh, that looks like an AR2 model. Or something that cut off after lag 3 for an ACF, you might say, oh, that's an MA3 model. Okay, so that's autoregressive models and moving average models. Now we're going to talk about those as the combined form. Oh, I guess first I'm going to talk about this briefly again. This is something that you will see in textbooks. People will even talk about this, but it is possible to write an ARP model as an MA model with infinite order Q. Immediately now, you're probably thinking to yourself, when am I going to need to know this, Mark? Never. But I think it's worthwhile to actually see. So let's talk about AR1 model, right? We've seen this a lot. Value today is just some fraction of yesterday plus some error. We know that if the absolute value of this thing is less than 1, that it's stationary. So let's just think about writing this thing out, right? If this at x at t is b times x at t minus 1, well, that means t minus 1 was just b times t minus 2, and t minus 2 is right. Everyone see where I'm going here? Okay, well, based on that, then we can essentially just do a large recursion here. So just take this thing and start substituting it in. Okay, so here I had it once, then I took that, I did it again, and now I'm just writing this out. So here's b2, xt minus 2, 1, 1, 1. And keep going and keep going and keep going. And what is this starting to look like now? Here's just our MA model, right? This is just nothing but a whole bunch of weighted error terms from past sequences, plus ultimately this autoregressive term. And over the long haul, that thing will essentially go away. Because in a stationary model, right here, we have this phi term. And we know that if it's stationary, this is going to be less than 1. The limit, as this thing gets really big, is 0. Okay, so basically what that means, so as k, this exponent gets really, really big, like infinity, this whole term goes to 0. And when that goes out, what do we have? We've got an MA model of order k, where k is essentially infinity. Okay, so basically that's all I did here, right? At that point, this term goes away and you have an MA model of order infinite to show that that's an AR1. I'll go through this quickly again. This is another thing that you hear people referring to, is this notion of invertibility. And this matters because of scaling. So the idea here is this term invertible. And what it means is an MAQ model, some moving average of any order, you pick some value you want. If you can write it as a stationary autoregressive process of infinite order, so now we're thinking about an MA model as a function of an AR model with infinite order, it's invertible. So basically, here's my my moving average model, which I've just written out simply like this. I've basically just taken this x to this side, the w to that side, and multiplied by -1. So if we sum over infinite orders and we had a bunch of coefficients, they're all minus in this thing because remember I moved this to the other side and multiplied both sides by -1. That's the only reason you get that. If you can do this, that's a question mark. This model is invertible. Okay, why does anyone care at all? Well, it helps us identify the model's parameters, and I'm going to show you an example of this to help motivate that. If we had an MA1 model, this first one here, we say x at t is wt plus 1/2 at wt minus 1, and wt was white noise with a variance of 25. This model is completely equivalent to this model, where I say x of t is wt plus 5 times wt minus 1. But here, this variance is 1. And the reason is, if you take right? So if this is known, so we have some value X, I should get rid of this. And we multiply, sorry, A times X. Does anyone remember what the variance of this new value is? Let's call that Y. And let's say the variance of X is sigma squared. The variance of this is going to be A squared times sigma squared. This is just, a lot of people think, oh, it's just A times the variance, it's A squared times the variance there. So all this is algebra. Because 5 times this value, that's just a simple white noise, is going to have the same overall variance as 1/5 times that thing that has very high variance. Right? These are completely equivalent. Yes.
Terms not change.
This one right here.
Yeah.
Yeah, over again, long time periods. We're thinking about, yeah, very long time periods. So yes. And the expectation of both of these is 0. So we don't generally think that it should affect that over the long run. Okay. Right, so we did this. So I'm showing you that these are equivalent. So here's the first one where it was 1/5 times of white noise with the variance of 25. If you do the calculations, what's the variance of X of T? It's 26. Because we saw that the variance of WT was 25. And here it's 1/5. So 1/5 squared is 1/25 times the variance of that, which is 25, is 1. What's the other one? Well, now we have that term squared, 25 times this variance, which is 1. So that's just 1 plus 25, which is 26. So they say they both have the same overall variance of X. So we know that we can rewrite these as an in terms of X. So if we go through that whole thing like we did with the AR process, and we're going to get down to here and write this thing out as a long AR model with some other terms for the moving average. We can keep going, we can keep going, we can keep going. If that theta, those coefficients, are less than 1 in absolute value, then we know that this limit holds, so that this term will essentially drop away. And we get this thing written out as this infinite order of AR models. Because this was the only moving average term in there and it just fell away. All we're left with is autoregressive terms. So there we are. I thought I had another slide in here. So this model right here, backing up. Right. If we can make this invertible, then it's easier to identify those parameters. That's really the only thing that matters. Most of you are thinking, how do I do that? Again, all of the software that you're going to use, any of it that you would be exposed to, at least in the R universe, is going to do all of this work for you. So that's really the only reason when you hear people talk about invertible MA models that you would really care. Okay. Autoregressive models. Let's get to those then finally. Questions about MA models, I guess, before I go on. Like I said, that's about as much as we're going to treat them in this class. Oh, sorry. Okay. So ARMA PQ models, autoregressive moving average, just has a little bit of both. You've got some autoregressive terms here up to some order P, and then you've got some moving average terms up to some order Q. And these themselves are not particularly common in ecology or environmental sciences. If they are, both of these orders are typically very small, 2 or 1, really quite simple. You can write those using a backshift operator. There's this really long equation right here, written much more compactly. Again, most of this is just sort of gee whiz stuff. All ARMA models are stationary. If all of those roots are greater than 1, just like it was for an AR1 model or an AR2 model. So now we're thinking about ARMA models. All ARMA models are invertible if theta be greater than 1. So you solve for the roots to get basically the phi's and the thetas. If every one of these is greater than 1, it's stationary. If every one of these is greater than 1, it's invertible. And again, this is just something that makes it easier for us to identify those parameters. Here's some examples of ARMA PQ models. ARMA 3-1, 2-2, 1-3, 2-2. And here I've just switched some of the signs. That P1 is a sign, a negative sign. So this has that very jagged up-down behavior that you see when the AR1 coefficient is negative. That's that. Otherwise, man, I'd have to squint for a long time to be able to tell you that those came from a different process. Here, here, and here. Look pretty similar to me. This would be another one too, where you could use your ACF and your PACF tools, we're going to see in a minute, to try to help you identify what these orders of P and Q are. So that you didn't have to set up this kind of massive search grid over all these orders of Q and all these orders of Q, and you're going to try to fit every one of those models and do it. Now that said, in today's age of microcomputers, that exercise would take your laptop 13 seconds to do for, yeah, I mean, not quite, but probably less than 1 minute and 30 seconds. So sometimes, you know, if you're like, I don't really know, just set up some exhaustive grid. That's fine. Here's the ACF for those. Again, for that one model that had a negative AR1 coefficient, you see this oscillatory behavior, up, down, up, down, up, down. All of these have relatively strong autocorrelation out to large lags, like 20, here's nearly 20. This one's a little bit shorter, like 7, 8. There's about 10. So you're like, whoa, okay, Mark, 25, maybe 27. I don't see an AR25 in here anywhere. So what's going on where? Well, it's an inexact science is basically what's going on. Here's the PACF for those. This one, ARMA 2-2, but I see significant correlation up to 4. Is it really that you add those? No. Because here it's only 3, and those added together would be 4. Here it's actually, there's some out here at like 7, so that's not it. So really what we're dealing with is this rather unpleasing anecdote of, yeah, tails off slowly. So if you have pure AR process or a pure MA process, the ACF and PACF work really well for helping you identify those. If it's mixed, you've got a little bit of work to do. Okay, I'm going to talk just briefly about non-stationary models. But before I do, I want to just check in with folks, how everyone feeling about ARMA PQ models. So far, so good. Like I said, AR models, in particular in environmental science, widely used. Moving averages or ARMA models, not nearly as much. Okay. Eli will talk some more about this as we start moving along. There's another class of models where we're going to introduce this little bit of integrated in there. So it's not an ARMA model, it's an ARMA is the way we pronounce that. So remember we talked about situations where you maybe had a time series and it looked like there was somewhat of a linear trend, maybe it was generally going up or going down, and you could difference that to remove that trend. You could difference something like this, or if it had that seasonal aspect, you could difference at roughly what the period was and it should get rid of that. It's the same notion with these ARMA and ARMA models. The idea is that if we did some amount of differencing, so now we're talking ARMA PDQ, so there's the AR order, MA order. Here's the number of differencing operations. So the idea is that inside here, we could say, what if we first difference this, first difference this, then second comma, fit an ARMA model to that. That's basically what's going on. So you could think of maybe D is 1. So we're going to fit an ARMA model to the first difference time series. So we're thinking about the, time to time change rather than the states themselves. Okay. So basically, if you apply some number of differences via a backshift, and let's just assume this is 1 right now. That makes this really easy. So we just backshift this thing 1 right here. Then this will be an ARMA PQ process. I'll show you how this works basically in a thing. So here is an ARMA model 1, 0. This is a really weird way of writing an AR1 model because I've explicitly said that the moving average term was 0. And in general, I just told you that we don't call models this where you have something. Well, let's just assume for now it is. So here's an ARMA 1, 0 or an AR1 process. Looks like this. So here, instead of just a phi, I have 1 plus. Okay. If phi is anything greater than 0, is this stationary? If it's greater than or equal to 0, stationary? AR1 model. What does this term have to be in its absolute value in order to be stationary? Less than 1. So this is less than or equal to 0. Is this stationary? I mean, greater than or equal to 0? No. Yeah. If that's 0 or anything larger, this is definitely not less than 1 in absolute value. Okay, so right now it's starting to look like that's not actually a stationary AR model. Okay, so here now, I'm just breaking these 2 terms out. So I've got this kind of funny AR model where it's got the x of t minus 1 in here twice. I'm just going to move this one over to this side. So essentially what I'm doing is first differencing this term. And here, now we can use a backshift operator. That's going to be just 1 because there is no backshift. Here, this is going to get replaced with b xt. Now we've got this. So that says that this process is essentially an ARMA 1, 1, 0 process, right? So that is, if I first difference this thing, what's left is basically this, an AR1. And this is easier to see with examples. So here on the top is an ARMA 110 model. So this now is basically, you can think of, I had a time series, I took the first difference of it. So now instead of those original estimates, I have the difference between every one of those estimates. Here's the ACF. Here now is an ARMA 10 model. So now I'm fitting an AR1 model to the first difference fit. And here's that ACF of this one, tails off much, much faster. This one I haven't messed around with at all. So these are probably real. Looks like 2 degrees or 2 lags with significant autocorrelation. Whoops. So basically, I thought I had another slide in here. These 2 are exactly equivalent. So you could take that original time series and fit an ARMA 110 model to it. Or you could first difference this and fit an AR1 model to it, and it's the exact same thing. This is something that you just have to probably take on faith right now and then think about this for a while. We can actually simulate this in lab. So when you see ARMA models, you can know that basically somewhere behind the scenes, there's some differencing going on, and then they're fitting some versions of ARMA PQ models. So oftentimes, if people think that maybe there's something going on, they just do the differencing themselves and then fit some version of ARMA model to the difference values. It feels a little less black box like to me. Gives you a full control over what's going on and you can see every step of the process. Okay, so today we reviewed white noise, random walks. And we spent quite a bit of time talking about this class of ARMA PQ models, either autoregressive moving average. And then you also saw how you can use the ACF and PACF for model ID. And as I said, you're not going to see a whole lot of this moving forward in this class, nor do I suspect you will see a lot of this in the literature that's most closely related to your fields. But you may. Questions about any of that? Stuff I could go back on, anything? Are we doing fine? Silence is deafening. Okay. Eli or Eric, did you have anything that you wanted to add?
Yes, so we're going to continue in this theme, but on Thursday, but you'll start to get like much more practical. We're going to look at, you know, how do you take a time series and decide which of these models to use, and kind of outline the classical strategy for that. And then with, like, as Mark mentioned, R is going to make this really easy for you. It's going to kind of do it for you, but you know, it's always good, like when you're using something like that, even though it is like a black box, it's much better to understand kind of what it is doing in the background, because it's doing the stuff that Mark is describing. And then for the lab, what you're going to do is you're going to take some real data and do some forecasting with this class of model. It's a really classic forecasting model, and actually for certain types of data, it does pretty well. And you'll, I'll also introduce a second type of classic time series model called an exponential smoothing model. And that's a type, it's kind of similar to these, but it evolves over time. And these models, even though like in the ecological literature, we don't really see these that much, except as the null model. You see them a lot as the null model that you test your forecast against. It can be sometimes pretty hard to beat these classic models in forecasting problems.
Do we have the meta-analysis that you two did with, was it with Jim and someone else, the one, right, where basically simple models go to the bottom line?
Yeah.
Yeah, I don't know if that's
We talk about that on Thursday.
Or we'll talk about it
Yeah.
later. It's like, especially when you add like covariates and environmental information. We think about like, well, we know that this variable should be important, so we'll add it to the model and it's going to improve things. But the cost of estimating parameters is really high. It's a lot higher than you might imagine. And you don't know the impact of, like, I'm going to say temperature. So you have to estimate what that impact is. And getting that estimate a little bit wrong adds error
we don't have it.
to your forecast.
We'll have to add it there. Yeah.
Complexity is costly. So we don't have.
Yeah, I wasn't, it's not on there. Anyway, yeah, they did a lot of work to basically prove that simple is good.
On the flip side, in ecology, we're often not doing forecasting. We are trying to understand what is it that caused these data? What hypotheses about how the system works are most consistent with the data we see? That's not a forecast. And these models that you've seen are not going to give you any information about that. Which is why when we go forward, we're going to be leaving these classic models, because even though they may be really good at short-term forecast problems, they're not going to help us in the kinds of questions we want to ask in ecology and fisheries.
Anything else from folks? Okay, thanks, everyone. See you Thursday. Thank you.